we need to think in terms of secant x being 1 over cosine x. So remember, SC, secant, cosine, cosecant, sine, CS, SC, CS. Okay, to remember this function. So how do I determine this? Well, I have to take it slowly. This is something called the inner function. Inner. This is the outer. When I evaluate, I always start with the inner function. I get whatever for this, and then I apply e, or I apply e to this power. But I have to find the power first to find e to this. If this is 2, then I'll say it's e squared. If this is 5, then I'll say e to the 5th, whatever. So I have to start with secant. So now let's take a look at this. And pi over 2 from the right, we have to picture the unit circle. So let's picture the unit circle. We know that pi over 2 is up here. Pi over 2 from the right means with angles higher than pi over 2. Which quadrant will have angles higher than pi over 2? Close to pi over 2, of course. Which quadrant will that be?
Second one?
Of course. So we are here. Now, cosine. What is the sign of cosine in the second quadrant? Remember, cosine is measured on the x-axis. So what is the sign of cosine?
Negative.
Yes. Good. So remember cosine. What is cosine at pi over 2? Cosine at pi over 2, how much? Anyone?
0.
Yes. So this is a problem. When x approaches pi over 2 from the right, 1 over cosine is 1 over 0, right? 1 over 0. No hope. Every time I get no hope, I know there are 3 possibilities. Which one? The numerator is positive. You already told me that cosine is negative in the second quadrant. So then now you can tell me where this piece is going. Where is it going? The top is positive. Say it again. I'm sorry, I just didn't hear. I talked at the same time with you. That's why I didn't hear. You are muted, maybe? You want to say it again?
Is it negative infinity?
Of course. Thank you very much. Indeed. Positive over negative. I have to choose one. Of course, it's negative infinity. Now, stay with me. We are talking about, so the answer is based on e to negative infinity. It's not legitimate to write this, but I'm going to write it. I'm going to erase it. That's very easy because I know how to graph this function. I know how it looks like. This is e to the x. So then can anyone give us the answer? Of e to negative infinity. What does it approach? From the graph, can we identify that?
0.
Yes, indeed. So for this function, x equals pi over 2 is a vertical asymptote. Sorry, I don't know why I wrote that. I was just thinking. It's not infinity. Infinity is over there, not here, not here. So there is indeed, it's a vertical asymptote for that, but not for the function we are looking at. There is no need. That's not the case. I got carried away. That's the function is e to sine x. It's e to secant x when x approaches pi over 2. Okay, this is not infinity. If this were infinity, I would have said that that is a horizontal asymptote, but that's not the case. Okay, so now let's look at one more. Let's say with something else like, I don't know, 38. Let me ask you if you have any questions. Any questions here before we continue? Any questions? Okay, so let's look at 38, see what this is all about. Limit as x approaches infinity, e to 3x minus e to negative 3x divided by e to 3x plus e to negative 3x. Okay. Like always, we have to see where this is going and where this is going. But first, let's start with these two pieces. They are the same. When x approaches infinity, where will these go? So remember, yes, because e to negative 3x is 1 over e to 3x. As x approaches infinity, this will approach infinity, and we know that 1 over infinity will approach 0. Excellent. So these are going to 0. Awesome. Good, so they don't count. So where is the numerator going? Anyone?
Infinity.
Good, over infinity. So it's one of the three indeterminate cases that we looked at. Very good. Jumping over this. So don't forget the limit operator, please. Since this is the most powerful, we are going to factor out the most powerful. It happens that it's the same in both. If it's not, I have to stick with what the powerful is for both. But it happens that they are the same. Can anyone tell us what to write here? And of course, eventually, that's what I wanted. That was my hope. Okay, so what do we have here and here? Anyone? Can anyone tell us? Of course, the first one is 1, right? And what about this piece? So that when I multiply these two pieces, I get e to negative 3x. What could it be? It has to be an e to which power? So when I copy the base and add the exponents, I get negative 3x. So this times this is that. This times this. I copy the base and add the exponents. And that's how I get the negative 3x. And the same thing with e to negative 6x in the denominator, of course. Do we agree with that? Do I need to explain more, or is this clear? Okay, good. So we already know where is this going and where is this going?
Zero.
So this is gone. Goodbye. This is gone. And the limit is 1. Did we use the symbol? The sign of infinity? No. So then this is y equals 1, horizontal asymptote. I'm thinking what will happen with negative infinity. To see, to be on the safe side, I have to investigate for such a function. Y equals 1 horizontal asymptote at infinity. I can take a look later on to see what happens to this. Okay, so I will look later on to see what happens with this. I never thought about it, so to see if it's legitimate to write it on both sides. So now this becomes 0. Yeah, potentially it will be on both sides, but I have to look. So for now, because this is not a rational function, again, it's a combo of a rational function with exponential. To be on the safe side, let's just not write horizontal asymptote at both sides, because that happens for sure for rational, pure rational, but a combo with an exponential may need to be investigated further. Okay. So what I would like to continue with, and I normally always, with all my classes, so sections 2.7 and 2.8, I present them together. And these are the last 2 sections of this chapter. Okay. Now, from everything we looked at so far, there were 2 major concepts that we looked at this class so far. Can anyone guess what those 2 concepts are? Something that I always said, it's major, it's major, it's major. Very important. Can you think of 2 concepts that we looked at? Big concepts, core situations that we looked at in this chapter. What was major in this chapter? So what was major? Major in this chapter that we looked at? That big line that crosses the graph of the function, and then we said, what if q gets closer and closer to p? What was that definition? Big definition. And we simplify it for rational functions, for quadratic functions, for radical functions. What was that big concept? Anyone?
Are you talking about the tangents and
Yes, but that big name that we calculated and simplified for many different types of functions. It was a big name. What did we say? What was that big name that we need to simplify, and then the terms without h at the top go away, and then h in the denominator has to go away? There are exactly 2 steps. What was that big name? What was the name of it? Anyone? Difference?
the difference quotient?
Yes, that's a big one. Difference quotient. So what are we trying to determine with the difference quotient? We are really trying to determine the slope of this line, which is the instantaneous rate of change. This is what we're trying with the difference quotient. Awesome. What was the other big concept that we talked about? In 2.2, in 2.3, in 2.4, in 2.5, they're all the same thing. Big concept again.
Limits?
Yes! Exactly. These are the two biggest concepts in this chapter. We learned a lot about limits. We learned 3 indeterminate cases so far. We have to add 4 more later on. Those are more difficult. Not by much, but they're more involved. Yes, these are the two concepts. When we apply the limit to the difference quotient, we get something very interesting. So these are the two concepts we discussed completely separate. We looked at this, and then we looked at this. Now we want to put these two together. So the limit of the difference quotient as h approaches 0 from f of x plus h minus f of x divided by h. This will give the instantaneous velocity, the instantaneous rate of change, instantaneous velocity. And it has a very special name and notation. Here's the notation. It's called the derivative first, let's say. The first derivative function of f of x. And this is the only definition. Okay, so I have a function. Why would I want to determine this? So here's a function, f of x equals, let's say, x squared plus 2x minus 3. This is quadratic. I want to determine this function for this function. I want to find the derivative, the first derivative. It's read f prime. F prime. So we want to find f prime, or the first derivative, for this function, for quadratic function. Why? Why would I be interested in determining the limit of the difference quotient for this function or any function? What's the use of it? Well, if we determine f prime, which we'll see in a moment, we're going to go through it, you will see the derivative of this function is 2x plus 2. You can say, did you make this up? No, you're going to understand very simple in the next chapter how this is done. What will this function give me? I'm happy with this. Why would I want to determine this? Here's one example. Let's suppose this is the distance function. If I determine this function, what will this become? By definition, what is the rate of change of distance with respect to time? What will this function? Yes, velocity. So this function, I'm going to write this down, f prime gives the instantaneous rate of change. F prime of x gives the instantaneous rate of change of f of x at any point where f of x, and this is an important word and concept, is differentiable. This is a full mouth, right?